Oh, Toby's not coming back.
Oh, okay. Is he okay?
Yes, he is lecturing computer science. I shit you not.
That is impressive.
Yeah. Worrying for the computer science people, but.
That'd be good. That'd be good. Okay. So to recap, we started to look at carts, classification and regression trees. So the whole idea is you make these decisions. You set it up, so you say, I want to do some prediction, and it's just a nice simple binary decision tree to decide which way you're going to go. And you can use that in classification or regression. But they have a problem. I mean, the advantage is when you give a decision tree to an end user, they really love it. It's how humans think, they love that idea. The problem is it's not a good way to model the problem. So let me illustrate this fact. So we're going to talk today about bagging, boosting, and then random forest. So we need to justify why I need to improve. What I've done here is I've taken the cardiac data and I've randomly split it into half. And then I made a tree on the first half, and I made a tree on the second half. And you can see, even though this was, to some extent, just the data is split in two, we get very, very different trees. Carts are really, really sensitive to your data set. They're very much, that flexibility, variability thing we've talked about, they're very highly variable. The nice thing is they can fit your data really, really good. They're unbiased, but they have a high variance. And this is just a nice, simple example. I mean, not even the first decision is the same. So how can we somehow take this nice user interface that is the cart, but make it a bit more on statistically solid ground? And what we're going to do is eventually get to, there's three methods we're going to look at: bagging, boosting, and random forest.
Is the prediction very variable as well?
Yes, it absolutely could be very variable. I mean, if you just looked at the flow down here with the same predictors, you'd get quite different results. So we're going to go back to first year stats, or second year, depending on when you hit it. So let's consider n independent observations, Z1 up to Zn. And I'm going to assume that they all have the same distribution. They're all normally distributed with the mean of mu and a variance of sigma squared. And hopefully, you could quite easily show, if I asked you to, that the variance of the sample mean, Z bar, is sigma squared on n. So what does that mean? If I take an individual variation that has a variability of sigma squared, as I take a load of them and put them together, add them all up and divide by how many, my variance goes down. It's reduced by this factor n. So the idea is that when you take the average of things, you reduce their variability. Make sense? So that's what bagging does. Bagging says, and you don't have to just do this for trees. Bagging is a general approach. Bagging says, let's say I had B separate training sets. What I could do is I could calculate B models, which I have to know. So I've got my first model. So I take my first training set, I make a model, which I call F hat 1. Then I get my second training set, I fit a model. So each of these models will give me predictions. Each of these models I could use to do predictions. And what I can do is now I can just add my models together. So in the case of a model that, for example, produces a continuous number in its prediction, I can take each of my separate models, feed in the predictors, get the value, add them together. And this is called bagging. What bagging is doing is he's saying, if I had lots of models and add them together, the variability of that would be less than a single one-off model. Yeah?
Can the training sets overlap?
I'm going to get to that now. So that's okay, but first of all, if you took your data and split it into B training sets, it seems a bit daft. So what we're going to do instead is we do not have B training sets, so we'll bootstrap instead. So what we're going to do, remember with bootstrap, is if I have n observations, I'm going to sample with replacement n observations. So that means that some points will not appear in my sampled data set, and some observations can appear more than once. So we sample them, and basically you go to data, let's say our data had 100 points. You'd sample 100 points with replacement, I'd fit my model, put that aside, go back, get another 100 observations, fit my model. And I'd end up with a load, in this case, B models. And then if I want to do a prediction, I would take my new point I want to predict for, feed it into each model, get the answer, average it.
Are we assuming that the models are the same in the sense that they're like all linear with the same number of predictors or not?
No, not necessarily. You just fit in your model. You could train your model, you can fit the whole process. There's no sense of they will always have the same predictors. In fact, they probably won't have the same predictors because maybe you don't get representation of that. So each time you're going to try and fit the best model, and then once you've got your model, you can fit your predictors, get your value out. All sounds like a bit of a con, doesn't it?
Yes.
Yes. It is, I'm sure it is. But it does. People do this. I've never done it personally myself. But we'll see in a second how this is a nice underlying foundation for random forests. Okay? So, let's do an example. So we're going to look at the Boston data set. The Boston data set is in the mass package, and it's looking at house prices. Altogether, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 predictors, which are the first 13 rows, and then we've got Med V. So these are what they call towns in Boston, so suburbs, basically. Now each suburb, they've measured various things about that suburb, and then the median house price, which is the Med V in thousands of dollars. And what we'd like to know is,
It's nice.
wow, I'm going to buy a house now.
I'm moving to Boston.
Yeah, I mean, this is old data. I mean, 24,000 is still very, 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 very cheap. And there's a variety of things in there, amount of crime, all the way to black was the number. There was a measure of however there was more black people or less black people in that neighborhood.
What is this color?
Yeah, I think it's the 70s. And as racist as it is, you will find that in a lot of states in America, if there's a large amount of basically different races in a neighborhood, it will increase or decrease the price. I'm not saying that's right or wrong, because I think it's wrong, but that's what the data says.
What is ZN?
What's what?
ZN.
Isn't he?
No idea. I can look up in the help bar, but no idea.
The number of
I don't care about ZM because when we start to do the prediction, it doesn't do anything.
I know, I was just curious why one was 18 and the rest was 0.
Yeah. Oh, there'll be more. I mean, these are just the first 6 rows. So there'll be, yeah.
zone maybe? Zone.
Oh,
Surely. As in like there was 0 through 20 zones or something? I don't know why they start at 0.
Everything starts at 0, that's how you count.
The proportion of the residential land zoned for lots over 25,000 square feet.
So how is 18 a proportion?
Unfortunately, as you can see, this description is not always really good. So, makes sense. NOx obviously is pollution in that area. But black, it's this, where BK is the proportion of blacks by town.
They have an equation for it.
It's important. Where does the 0.63 come from?
L stat is the lower status of the population. Now, I assume by lower status they mean lower socioeconomic, but I'm sure by these, let's face it, racists, they just mean that they're lower people somehow. So, not my favourite data set, to be honest.
Proportion of blacks.
This is fantastic.
Yes, so.
It might not affect the prediction.
I like it. Well, I find, where does the 0.63 come from? Was it like the average? The median?
I think that would be the average for the whole population.
It's
Yeah.
very high.
This was in Boston. I don't know if Boston particularly high or low representation African Americans.
Anyway, sorry, I'm getting distracted.
No, it's good. It's good to think about the data. I mean, in the future, I'm using this data set. It's one that the textbook used, Personally, I don't want to use this textbook because I somehow feel that like it's just inappropriate.
Yeah.
But then
Maybe we
the
should remove
data's
that one
the
dark
data.
column.
Oh.
The data's the data. It's
Yeah, but no, it's an ethics. This gets into ethics. If data is unethical, should you use it or not?
Well, in your next lecture, just for the sake of the lecture, just remove that column and save you 10 minutes of conversation.
So, how do we do it? Well, I'm actually going to use, I know this is a bit daft, I'm going to use the random forest. Because I can use random forest, as we'll see later, to actually do bagging. And the key thing here is when I use the random forest, my predictor, I've got to use everything, so I've got the tilde dot. My data is Boston. The m trie equals 13 says, and I'll explain this in more detail later, use every predictor. And when we get to random forest, you'll understand why the m trie I've actually put in there. But if I say use every predictor, it will give me bagging. Okay? And I'll explain that. I know it's a bit backwards, but you sort of need bagging to get random forest, but to do bagging, you need the random forest. And it's confusing. But I'm also going to compare this with just a single tree. So I've got a single tree where I'm doing the median house price on every other thing, so we can do a comparison. Okay. So, first of all, here's my tree. Now, obviously with my bagging, I'm not going to get a single tree. For every model I fit, I'm going to get an individual tree, so you don't get, you could go and grab each of them trees and start comparing, but you're not going to get a single tree. Remember what it's done is it's gone to the data set, it's sampled a number of rows with replacements, so you have the same number of observations, and it fitted a tree. And it's done that numerous times. In this case, it doesn't do any pruning, it just takes the overfitted tree, because it's saying, I'm going to do lots and lots of these, usually about 200, and I'm just going to aggregate the results.
So when you say with replacement, do you mean that each bag can narrow more than once?
Yes.
Okay.
Because it'd be like me coming to here and saying, I want you lot to represent my population. I've got 1, 2, 3, 4, 5, 6, 7, 8 people. I'm going to replace that with 8 observations. You might appear twice. Because I'm doing sampling with replacement.
Okay, that seems even good.
Yeah, that's just, I mean, that comes back to the bootstrapping. Remember when we did the bootstrapping? And we did sampling with replacement. I love when students look blank as if they've never seen me before. And I go, do you remember? And they go, fuck, I don't remember who you are. I just woke up at this moment. This is it. There is nothing before this moment in my life. This is the matrix. Bang, we all appeared in this room. I don't know what you're thinking about yesterday, Jono. There was no yesterday. Just, it's the...
Before the holidays. Give us some slack.
God.
Come on.
It's before the holidays for me. I don't sort of go ching and wake up and just go, oh, I don't know who I am. Let me see. Oh, I'm slightly fat and I've got a funny accent. Well, fuck, that's a change. Gosh, true. So here's the tree. If I just ran tree, remember with the bagging, I'm going to have lots and lots of these, and we're going to put them together. So what I've done here is I said, right, let's predict using the tree, and let's predict using the bagged trees. And then all I've done is I've looked at the sum of squares. Because by the logic of that previous thing, the residual sum of squares should go down. The whole idea is the variability goes down by basically making lots of trees and putting it together. I.e., the prediction got better.
What are you doing for the bag one? I know you've done like the bootstrapping to get your B sums
Yep.
and that, but then what are you doing?
Then I go and I say, right, let's take an individual observation, shove it in the first model. What does it say the median value is? Go to the second model,
Models.
each of the trees. So I have altogether 200 trees.
Big forest.
Yeah, so I get some data, I just put it in what it's doing in the background, I put it in and I get a tree.
Okay.
So I'm going to get something that's going to look like this, but I'm going to get 200 of them.
Okay.
Then you can come to your first observation in your total data and say, what do you predict is the house price? And it will go to the first model, which will be a tree like this, and it will go down and it might predict, say, 45.58.
Okay.
Then it goes to the second tree, repeat it, and then it will just average them results.
Yeah.
And the key idea here is if I look at the square difference between the true median house price and what I get from just a single tree, I get this measure of how good it is. Well, if I do it with the bagged, I now get a smaller residual sum of squares. So the amount of variability is decreased.
But does your time to compute this increase?
Yes.
Because now you're creating like 200 trees,
Yes.
that seems like a lot.
Yeah, it's still pretty fast. Luckily, cars are pretty fast.
Okay.
But yes, you have a computational cost, absolutely. That's fine when we talk about the average. You know, each tree can predict the value. I can take the average. What you do with classification? You go to each tree and you say, what level do you classify this as? And then our final prediction for putting all the models together is we use the most common prediction for that predictor. Make sense? So it's the most commonly occurring one. So here is me just doing the similar thing for classification, where we've gone back to the heart data. And again, you can just, and you don't need to change anything. All I have to do is make sure, just so happens that the number of predictors in my heart data was also 13.
Is there a way to automatically do that, or do you actually have to know how many predictors you have?
You have to know how many predictors you have.
You could just do n cold minus 1 heart.
Yeah. Yeah.
N cold heart minus 1. You can do it.
Yeah. It's a shame it doesn't have, I mean, if I was writing this function, I would have a thing called comma bagged equals true. And underneath I just do the calculation. I think it says a lot about the bag, the fact there isn't a bagged function.
Yeah.
The fact that you're actually taking random forest and basically breaking it to get it to work is probably an indication that it's not a thing we really do. And we'll see in a second why we don't do it. Okay. Go on. Talk amongst yourselves. Tell me what this code is doing. That's the proper name. That's not a thing I'm making up.
Isn't it?
No.
Oh.
Okay. The interesting thing, this code just does something very simple. It takes n numbers, and first of all it samples them with replacement. And then it says, how many numbers have not been counted? Not just do it numerous times. And what do you notice? That generally, on average, there's about, let's say about a third. About a third of the observations, whenever you do sample without replacement, end up not being sampled. Okay? So, you know, there's actually this idea of, well, every time we do this, every time I go and get a bootstrap sample, there's a proportion that don't get sampled. There's a portion that do. You can actually prove this result. It's just a probability calculation. But let me summarize it. On average, each bag tree, in fact any bootstrap sample, uses about 2/3 of the observations. So if you think about it, we automatically, by the random chance of sampling without replacement, have the equivalent of cross-validation. On average, 2/3 of the observations get used to build the tree, and another third, just by random sample, don't get chosen.
Sorry, so we're taking n random samples from n values.
Now I'm taking a random sample of size n from n observations.
Yeah, that's what I just said.
No. You said n random samples.
That's different?
Yeah,
Okay.
very different.
So we're taking a random sample of size n from n observations?
Yes.
Replacement.
With replacement.
Yep.
And on average, approximately a third of the observations will not be in that bootstrap sample. So I can automatically use these as a cross-validation error. Because I take my tree, I've got a third of my observations I've automatically taken aside just by random chance. So I will just quickly take that tree, predict it for these values, work out the values I get, use that as a basic cross-validation error. And this is called the out-of-the-bag error estimation. You get a built-in cross-validation automatically by the nature of the process. The other thing, so the problem we've got at the moment, we've got these lots of trees, but imagine someone came along and went, that's really, really good, John. That's really cool. I've got this big forest of trees, but please tell me, does this predictor have a significant effect or not? We've lost that explanatory nature by having multiple trees. I can do prediction. I just feed it into every one of my trees and get a prediction put together. But what about explanation? Well, they have a thing called a variable importance measure. And basically, you can look at every tree and you can look at every time you have a particular predictor in there, and you can ask the question, how much do you improve your fit when you go through that split? Or as it says there, we can either look at the residual sum of squares or the Gini, which is that Gini index, the classification. We can look at the total amount it decreases the splits associated with that variable. So you go to every single tree. As you go through a split that involves a particular predictor, you can look at the decrease in residual sum of squares or Gini. Gini if it's classification, residual sum of squares if it's regression. And that will give you an idea. So if there's a large amount of decrease, it's a better predictor. So here's the variance importance plot for Boston, and you can see that RM and L stat. So RM is the number of rooms, and L stat is the lower status of that suburb. And these have a big effect. These are the ones where you have, every time you had a tree with one of these predictors as a split, you found that once you did the split, there was a big decrease in RSS or a big decrease in the Gini index.
So the more along the right it is, the more important.
Yeah, basically, all these are important predictors. They made a big difference when they were included in a model. So that's one way you can measure your variable importance. So in this case, if they came along and said, which are the two best predictors of median house value, you'd go rooms and lower status.
She probably couldn't guess.
Yeah, it passed the stupidity test. And as you can see, ZN, your zone, really makes much difference. And to answer our question of, does
racism help with picking prices?
Luckily, no.
Well, what's LSTAT though?
Lower status. It's more about common folk like I am than different races.
So that could also be like a proxy variable for.
Could be. With the heart, again, I did a similar thing. So this one is the Gini, the mean decrease in Gini. The thallium, remember that was where we injected a thallium, which is a dye into your blood, and look at the results of that, and then look for heart defects, etc. Whether you have chest pain and your calcium levels. These are the three big predictors of whether you're having basically myocardial infarction or not. So now boosting. So the first one, we just basically took our data, we sampled with replacement, we fit lots of trees, and then we aggregated those results together. And the idea being that the average of our predictions will be less variable, hopefully, than individual predictions. So we've sort of had a way of dealing with that variability, so right at the start where we had two data sets split and we got very different results. Boosting. We're again going to grow multiple trees, but this time we're going to grow them sequentially. We're going to start with a tree, and then we're sort of going to go, where's that tree failing? Can I improve it a little bit? Where's that? These two trees failing, can I improve it? So it's a guided improvement at each stage. We're going to make very small trees, and all the time we're going to say, what areas did I cover? Let's improve it. This is called boosting. So we're going to grow each tree, it's going to be grown using the information from the previously grown trees. So, how do we do it? Our first tree we're going to do here, we're just going to set our prediction equal to 0, and we're going to set our R equal to the data itself. And then what we do is, we're going to do this B times. We're going to fit a tree to R. So right at the start, our first R is just the data itself. And I'm going to fit a tree, and I'm going to limit the number of splits to something small, maybe 3 or 4. So I'm going to end up with 4 or 5 leaves on my tree. So I fit this tree to my predictors R, and this, so my predictor is X and my response variable is just going to be, to start off with, the response variables in the data. Then, I create my new tree by taking whatever previous tree I had before, so the first one was a 0, but then I'll slowly add up these trees, and I'm going to add in a new tree, but I'm going to take a tuning parameter, or lambda, of that tree. So it's a linear combination. So each time, I start with a tree, and I'm going to add in a new tree, but I'll weight it down a little bit as I go further along. And then what I do is I'm going to get these new residuals where I take the data, the response variable, and I take off what is predicted by the previous tree. So you start with right at the start, you have all your predictors and your data, and you fit a very small tree. And then you take that small tree and you go predict the actual response variables, and it predicts it. And some, it will get really good. It will get really, really close. Our residual will be 0 because I predicted exactly the value that the response variable was. But some it really misses. Some it's a long way away. My tree missed and hence the residual is large. These are now going to go in as my response variables to fit the next tree. Same predictors, new response variables. I fit a tree. And then get the residuals, which is what is the difference between each of my response variables and what the tree predicts it should be. I take them values and I fit. So it's almost like I go, here's my model. Where did it fuck up? I find all the values where it has a really large residual. A large residual means the model just failed for them. I go, right, I now fit a model looking at the bits where I made a mess. Because they're the ones that are going to have the big response variables, which in this case is the residual. Look at that, take that off. Now let's fit a model that gets it. Every time I'm going, where did I miss? Where's the areas where I still have some difference between the true response variable and what my models are predicting? And all I'm doing is each time, instead of just starting with a brand new model, I just take the one, I go, well, that was okay. That got, 10% of the observations spot on. I'll add this new tree and I'll weight it by a lambda. So you're building these sequential trees where each point I'm going, where did I miss? Where I missed will have large residuals. Let's use that as my new response and try and find a tree that's really good at predicting the bit I missed. And you're just building this up. So it's called boosting.
Can we fit trees with a different number of terminal nodes, or they're the same size tree?
In this so far, the ones I've looked at, the built-in one goes, I want the same tree size each time, the same lambda each time. So you have, we'll get to it, you have 3 parameters you can choose. Your lambda, which is how much you're sort of adding the new bit on, the size, the splits, and the number of trees that you want. So, here's the goal of boosting. We slowly improve the model by using the areas that it does not work well to fit a slightly new model. And I'm just adding that on. So getting to your question, so nicely done, Josh. Tuning parameters. There's 3 main tuning parameters in this. There's the number of trees, because if you just keep growing and growing and growing, you're eventually going to overfit. Your final tree is just going to go, there's just one observation you didn't quite get right. Because remember, you've got all the other ones right by now. Let's just fit that perfectly with this one-off tree. So you don't want to get too many. Remember, this is not a matter of just decreasing variability. You're building these trees up slowly, so you can overfit. You've got your shrinkage parameter, which is the rate at which learning occurs, and you've got the number of splits. The number of splits seems to be really small. When I looked at the literature, everyone seemed to be using just like 2 or 3 splits, just to make it fast. It was easy just to go, have a tree with just, 4 nodes, 4 nodes, 4 nodes, just do it fast.
So at the end, we take the linear combination of the trees with the shrinkage.
Yeah, so it's weighting down as you go every time.
It doesn't converge to a good tree, that does it? Because each new tree you create just deals with mistakes the previous.
If I let B get large, it would converge to a perfect overly fitted tree, where each point would be predicted by its exact value in the training set.
Yeah, so the linear combination would converge to that.
Yes.
But like the capital Beef tree you fit,
Yeah.
that has no meaning on the data.
No. That basically, the beef tree would be the best small tree that fits the bits you've missed so far before.
So you're just correcting each time.
Yeah. And it doesn't just have to be trees. You could do this boosting with other methodologies as well, but it seems to be mainly used in trees. So you could have other models where you go, fit the model, where did it fit? Let's improve it with a new sort of weighted regression. How do you do it? There's a GBM package. In this case, I said the distribution on is Gaussian, the data, usual formula notation, here's my shrinkage and my interaction depth. Interaction depth, if I remember rightly, was the equivalent to the number of splits. And in this case, 100 iterations. There were 30 predictors of which 8 had a non-zero influence. So again, you can do inference measures, etc. I couldn't find out how they do the inference measures in boosting, I'm afraid. There was no easy way to find it. It didn't seem to do it out of the bag that I could see. So that's bagging and boosting. Here's our summary. Again, it's always nice, remember, model early, model often, all models are wrong, some are useful. I love when you fit different things and you find the same pattern again and again. It makes me less worried. We still find, if you look here at our influence, our LSTAT and our room is still important. It always scares me that you fit some other model and you find a different result. That basically says all my results are probably just noise. Consistent results makes me sleep better at night. The other nice thing this one has is it has what they call a partial dependence plot. So before we said rooms have an effect, but what do they have an effect? This will actually marginalize over all the other predictors. So this is basically giving me a marginal effect. You can see as the number of rooms increases, the median house price increases.
Does 9 seem like a lot of rooms?
Fun?
How do they, does 9 seem like a lot of rooms to you?
Yes, but I don't know how Boston does. Maybe they have these very big houses, or maybe.
Rooms.
Yeah.
Yeah, but what if you live in living room and have open plan living and you've got 3 rooms in your big house, it's just...
Would they do that in some ways?
Just 9 seems like a lot. You got 4 bedrooms and then a bathroom, that's 5. What are the other 4? Luxury.
Kitchen.
Yeah.
Yeah.
Well,
Kitchen, lounge,
Yeah,
study.
yeah.
Then you've got another 4, so you've got your 7. A couple of bathrooms. It's
Laundry if you really want.
yeah.
Basement.
Yeah. And LSTAT, as that increases, your price goes down. So as your lower status of the neighbourhood. What lower status really means, I don't know. I could go and read that paper, but I'm sure I'd get cross reading that paper.
Probably more poor people, right?
Yeah. Lower status, I think, will be more lower social economic area. So now we get to random forests. Okay. So let's start recapping that idea that if I've got the IID variables, so independent, identically distributed, they all have a variance sigma squared, then we know the variance of the sample mean equals sigma squared over b. So just place that in with b. And fine. As our sample size gets larger and larger, our variability goes down. Fine. What about I just change one thing? I've got B, now they're identically distributed, but they're not independent. They have some sort of positive pairwise correlation. Right. So they're related. They're related in a linear sense. You can show, and I think it's going to be a great thing for you to do on your own at some point, that the variance of the sample mean now is not our sigma squared over B. It's now rho sigma squared plus 1 minus rho over B sigma squared.
Exam question.
Oh, I hope so. That'd be just lovely. What would you do for the other 4 hours?
Sit there and marvel at the beauty of the answer.
Yeah, just marvel. Just go, that's fantastic.
Wait, 4 hours?
Well,
The upper 4 hours?
yeah. Well, that would take you at least an hour.
So you have a 5-hour exam?
Well, the first half. I mean, there's got to be a break. You've got to, after 5 hours, have a break.
quick snack and a drink and get back into it.
Yeah, and some people will just start running away and never come back. I mean, also you've got to move to the obstacle course. I mean, you can't have the obstacle course and the exam in the same place. We're not allowed to do that.
In Imperial China, we actually had exams that went on for multiple days. I used to sleep in the exam cubicle.
Fuck. I thought my finals were bad. I once had an oral exam that went on for 3 hours. 3 hours of being sat there and being grilled by someone non-stop about whatever. And they said, we can ask you anything you've learned in the last 5 years. And I said, well, that won't take 3 hours. 1 minute. But yeah, they would just sit you there. In fact, they take it in turns. I remember one of my medicine exams, they sat there, and at one point they went, what's this? I went, what? It's an x-ray. Of what? It's a rabbit. Why is this x-ray important? It turns out it's one of the few x-rays of calicivirus in the rabbits, a condition that hadn't been seen in the UK at that point. It had only become notifiable the week before.
That's massive.
Yeah, fuck 'em, I knew it as well. Oh yeah, it's a rabbit calicivirus. That's why I failed the first time. It seems you're not allowed to do a victory dance in the middle of an oral exam. So what does this mean? I mean, one, you'll get to prove it at some point in the near future, but what does it actually mean? Well, it means however big your B gets, there's a lower bound. The whole idea of bagging was, let's get lots of samples that reduces the variance. This one says, as long as they're independent. If they're not independent, you're going to get bound. Your variability is not going to get low. Okay? So this is a problem. Why is it a problem? Go back to bagging. Let's imagine we have really one very strong predictor. Then all these trees are going to have these predictors. They're all going to be correlated. The problem with bagging is the trees can be very correlated. They're all very, very similar. They're all very, very similar. You just get the same result again and again. You're getting low variability, but it's not actually existing. So what we want to do, the key idea of a random forest is we'd like to do bagging, but we'd like to decorrelate the trees. We'd like to remove this dependency structure. And that's what random forest does, it decorrelates the trees. First of all, as in bagging, we're going to take a random sample, the same size as data, by sampling with replacement. So that's the first randomness. But when we go to the trees, each time we come to do it, instead of choosing every predictor, we're going to randomly choose M of the predictors to choose to decide what to split on. So you come to the first split, and instead of going, right, I've got all 13 predictors, you randomly choose 4 and say, these 4 predictors, which is the best one? Then you come to the next split, you go back and you re-choose. You don't use the same 4 predictors, you go and re-choose M of the predictors. So we're randomly choosing the observations, and at each split, we're randomly choosing the predictors to have in there. That means that if there's one strong predictor, there's a lot of chance that it won't get even included in the first one to choose. So you bootstrap your samples, you randomly choose your predictors, you fit a split, then you go back, you've still got the same, so you keep the same observations as you fit the tree, but each time you come to a cut, you randomly choose which predictors to consider in that cut.
So we're not considering the same predictors for the whole tree?
No.
Okay.
No. So you come to the first one, maybe the first one you say, right, I choose 4, and maybe it goes, right, room, LSTAT, blah, blah, blah. I choose which of them 4 is the best to split on. And I come to the next split, and I go and randomly choose 4. And some could be repeated, some could be new. But it's not, each time I make a split, I randomly choose the predictors I will consider.
Could you get to a point though where it keeps like choosing ones they've already done and there's no good way to split on those, but there could have still been splits on others?
Yeah, remember, it's always a greedy algorithm. There's always the possibility that you could have had something better if you'd been a bit cleverer.
Okay. Also, how do you choose M?
Get back to that later. We have rules of thumb.
It seems too convenient to be true that works.
It just decorrelates them. I mean, they sort of went, bagging's good, multiple trees is good, but we find that we get the same tree all the time if you have a strong predictor. So this way we just, by adding this randomness, decorrelate the trees. By decorrelating the trees, That signal, if it gets closer to 0, if it gets closer to 0, we can decrease the variability.
So any one of these trees can just be rubbish, right? If you get
Yeah.
unlucky, then some of them will just be.
Absolutely, you've got lots of trees.
Yeah.
Hence random forest.
You still take like the same number of trees as in your baggage, or do you have to take more, or?
There isn't any indication on that. I just used the default built-in, which is about 200.
So you know before when we like prune a tree, do we deforest forests or not?
No one seems to. No one, they basically let it overfit and then just put them all together.
You don't want to like take out the crap ones?
How are you going to judge a crap one? You mean like take the top so many on an RSS?
Possibly.
Not seen anyone do it, but it's a good idea. So now you see where the M try. The M try is how many predictors you're going to try in each cut within each tree. Hence the one before where I had M try equals 13 means you're going to choose 13 of the 13 predictors. Hence you're not doing this randomization part.
Then you're not specifying the tree depth.
No, what it does normally with bagging, remember we've gone beyond boosting with bagging, it basically overfits it. It will go down to, usually the cutoff is either a number of pieces in RSS or the number of nodes.
Yeah, okay.
Sorry, the number of observations in each node. You can still do your variance important plot. Remember the amount that you decrease in RSS or Gini each time a predictor is associated with a split. Luckily, it still helps that an RM is still there. We all feel comfortable. I know it all seems like black magic, not the good black magic, but it seems a bit weird. But the good thing is, it still seems to be giving consistent results. Nothing we've done has said a complete change to the results. So you can look at your importance, but they have another importance. If you think so far you've been a bit confused, let's confuse you even more. We have an out of the bag variance important measure. So you take your Beath tree, you fitted your Beath tree, and you predict for the values that weren't included, the observations that weren't included in that tree. Remember the idea is roughly 2/3 are included on average and 1/3 are not. And you measure how good this tree is at predicting that individual prediction. Then what you do is you go to the jth variable, you permute it, and you refit the tree and see how things change. So you've got this variable that says, yes, I'm a good predictor. If I go permuting it and it makes no difference to the overall fit, obviously it wasn't that good.
What do you mean by permute?
I mean, you take that column and you just rearrange all the values. So every value appears once and only once. You have just done basically a sample without replacement for exactly the same things. All that's done is you've gone to that particular variable and you've just changed the order. So it might be that some houses now that before had 9 now have 2 or vice versa. You've just permuted it. You've just made it noise and said, now how do you fit? So you're looking at the change in your fit when you go from having the observed value and having just noise.
And so you keep the rows in the same order and you just shuffle one column.
Yes.
For last. Okay.
Yeah.
Good.
We only do that once for each tree.
Yes. Well, for each variable within each tree. And then you go to the next tree, and for each variable in that tree, you'd do it. And each
You
time,
permute one variable at a time.
yes. Yeah, I mean, you don't do all this. People cleverer than me, not cleverer than you, but cleverer than me, basically said you put importance equals true, and it basically does it all for you. And now when you do your importance plot, you can see you've got the one we had before, which was the known impurity. You've got this new one, the out of the bag. Again, you know, it looks pretty much the same. Down at the bottom, there might be some change in the order. You see that Chaz and ZN, they've changed. But the ones at the top, the room and the Elstat, haven't. What was that?
What's Chaz?
I don't know. It's probably some sort of racial slur.
That's just some guy called Chad.
Charles River.
It's the Charles River dummy variable.
I thought you kind of cool though.
I assume that means whether your suburb is on or not on the Charles River. I assume the
That
Charles.
would increase your value, because like living in rivers is nice.
Yeah, that doesn't say whether it increases or well. Yeah, it seems not.
Apparently not.
Maybe it floods a lot.
Maybe.
Yeah. Going back to your question, what are your guidelines? Rough rule of thumb. Classification. You take the floor of the square root of p. So you take p is your number of predictors, you take the square root, you just floor that to make it into an integer. Well, regression default is p over 3. And notice we asked you before how you fit the tree. We have the minimum node size. So they're actually completely overfitting down to 1.
What's
Yeah.
the difference between classification and regression?
Classification is where the thing you're trying to predict is a categorical variable.
Okay.
Regression is where the thing you're trying to predict is a quantitative number, basically. So we call these general regression.
And why is there a difference for the end value?
No idea. This was just the guidelines. The original stuff on random forest was by Greenman. I don't know about you lot, but I once read Greenman's paper, and I think he might personally hate me. It was horrendous. So it will be rules of thumb.
Could be that for regression, if you have a large number of predictors, you want to fit, you want to have more options to choose from because you can go further down.
Yeah. I mean, I would guess that it comes down to some sort of idea about what's the largest size you can get away with but still decorrelate. So it might come from a probability argument.
Was it the same argument as well? You just wanted 5 as significance.
What, because Fisher said so?
No, he used it once and it seemed to work.
Yeah.
Like, yeah, fair enough.
Yeah.
But classification would overfit faster, right? Because it's like a discretized thing at the end, whereas the regression.
In theory, you can keep going more and more. It gives
Yeah.
you smaller bands.
Yeah. These were just recorded in James, just in case you need to ever do it. So here's an example with the heart disease. And again, okay, they do change the order of the top 3. But generally in this you find that, it's changed the order, but they're still pretty equivalent. Calcium, thallium, and chest pain. So again, various important parts. And that is it. That is all the adaptations you can do. You've now got bagging, boosting, and random forest. Random forest is the big thing. Everyone seems to be using random forest.
So it's just one of these things where like I had to tell you about bagging and boosting, but don't use them.
No, I mean, personally I would use random forest. I think random forest is the most complete, it's the most understood. But sometimes when you do data science, you use whatever method that either your supervisor is used to or the literature is done. So one of the things that, I've mentioned this before, is often I do these methods because there's already a paper in that field that uses this method and it's been accepted. I have used random forest for looking at chronic fibromyalgia. And a lot of that was because the person said, but there's another paper out there that uses random forest. So we went and learned random forest and used random forest. Bagging and boosting are really nice ideas that will come up again and again. So they're more foundational. I wouldn't necessarily use them for trees, but you'll start to see in any ensemble methods, bagging and boosting are things that you should know about. So I see bagging and boosting as more foundational. Random forest is the one I would use.
You can't let the principle of random forest and apply it to anything other than trees.
Reply it to what?
You can't take the principle of random forest and apply it to any other models other than trees because you don't have that sort of at each node choose for yourself. Unless you were fitting.
Yeah, you could definitely do some sort of linear regression where you randomly select the predictors in and you had lots and lots of models. I mean, bagging and boosting definitely could be applied to linear regression.
I agree. Sort of forest is a bit more difficult. So.
Why not? I mean, why not do it and just say if you had big prediction, you could decorrelate it by doing a random selection. You wouldn't be doing each split, you'd just be randomly selecting at the start. I mean, to some extent, A-Line's doing something similar, but she does hypercube, so she has a deterministic choice of what predictors to have in there. But we could have a thing where we have a stochastic.
There you go, there's some more work for you to do.
By the way,
Yeah. So I mean, it's an idea where if you could take, especially if you don't have enough predictors. Sorry, you don't have enough observations for all the predictors. So you have n much less than p, which is what you get in genetics. You can now stochastically choose. The hypercube just gives you a nice deterministic system.
Honestly, probably doesn't make much sense. Could you do it in a way where like you fit your intercept and then for your it's done.
No, I mean this is how new research comes along. Someone goes and says, "Could you do this?" and they try it, and then the big question, you said right at the start is, well, if you have this idea, will it work? And now you've got different ways of going, will it work? You can go and do the theoretical show the asymptotic behaviors and stuff like that. Sometimes you do simulations. The question is, does it work better? So like, for example, with A-line stuff, we'd say, well, is stochastic somehow better than the hypercube process? So now you have to, so they're all good ideas. There's nothing wrong with having an idea and seeing how it goes.
That one wasn't a bad idea. So.
Cool. On Wednesday, we'll do support vector machines. If you think this fucks you up in the head, you wait till we get to support vector machines. That's proper fuck in the head syndrome. It's great. It's just lines, but in a fucked up dimensional space. It's brilliant.
Would that be the hardest thing in this course? Support vector machine.
I think in the abstract nature of what it's doing, maybe, yes. I don't know. I think everything the first time you see it is hard. The second and third time, the tin's been loosened, it's a bit easier. But I think bootstrapping that idea of like sampling with replacement intuitively doesn't make sense. You seem to be double dipping. But there's a lot of statistics which is double dipping. So, cool. See you all Wednesday. So I haven't marked your assignments. I'm going to try and do it all tonight.
How was the cursed child?
How was?
The cursed child.
Oh, fantastic. Just brilliant. It's a long time. I have been to something where I think that was so worth travelling all the way to Melbourne to spend a fortune, to spend probably 5 hours in the theatre.
Oh, 2 parts, yeah.
2 parts. Absolutely just magical. I highly recommend it. Put it this way, in the 2 things I've seen in the last month, it was the better one, and I'm comparing it to Endgame.
Which was a pretty good movie.
Yeah.
Especially when everyone died at the end.
Yeah. I can't believe they introduced Batman and fucking killed him all in the same time.
So unnecessary.
At last they got it right.
And then when Superman saves the day.
Well, I hate that. I hate when Superman saves the day.
This is like